today. All right, today we're talking about momentum. I'm going to start talking about it. It's going to be pretty much all week we'll talk about it. You saw I posted your week at a glance. Sorry I missed that last week. That might be slightly subject to change depending on how the week goes. But today and tomorrow and Wednesday will definitely be the same. So the Big Mo. When I think of momentum, I think of Missouri, University of Missouri, the band, the marching band, one of their drums, it says the Big Mo for the Big Momentum. I'm a nerd. I like sports. All right. Momentum is defined as, is a weird definition, but it's defined as the product of an object's mass and velocity. It's a product of the object mass and velocity. It is a vector. Now, why is it a vector? Because of direction. Which part of momentum has direction? Mass or velocity? Velocity. Since velocity has a direction, it would also have a direction in it. Momentum what? It does not have a good unit. It does not have a good unit like forces in newtons. Energy is in something else. It's in joules. Momentum's units are exactly what it says: kilograms times meters per second. They don't have anything really with that. A couple things that the mass needs to be in kilograms and the velocity needs to be in meters per second. Symbolically, momentum is P. Momentum is P. So P equals mv. I don't know why. I mean, M's already taken. M is already taken, but I don't know why. I don't really know where the P comes from. But momentum P equals mv. Momentum equals mass times velocity. Momentum, you can think of it as momentum in inertia in motion. Momentum is inertia in motion. Okay. We talked about Newton's. When we talked about Newton's first law, an object in motion will stay in motion, or object in rest will stay at rest. Okay. Who's going to have more momentum, myself or Drew? If we're running at the same speed, it's going to be harder to stop me. Okay. We're going to talk about that today in braking distance. Okay. But momentum is inertia in motion. Now, a question I have on there: will a large truck always have more momentum than a roller skater? Yes or no? Will a large truck always have more momentum than a roller skater? Who thinks that the truck will always have a larger momentum? Raise your hand. Who thinks the roller skater will always have a larger momentum?
I'll raise my hand.
Wait, so is it choose an option or is it depends?
It depends. It depends, okay? If they're moving at the same speed, who will have the greater momentum? The truck, because it has more mass, okay? But however, what if the truck is stopped and the roller skater is moving? Momentum has to be moving, okay? Momentum has to be moving. So if the truck's not moving, does it have any momentum? No. So in that case, a roller skater who is moving, even if they're moving at an extremely slow rate, will still have a greater momentum, okay? So it's a product of mass and velocity. It has to be moving, and you can make the roller skater have more momentum, okay? By either going fast, it has to go a whole lot faster, but if it's not moving, it would. What changes momentum? Momentum changes, either the mass or the velocity changes, okay? Now, most of the time, you don't change the mass of something, do you? I mean, I'm not going to change my mass and change my momentum, okay? How am I going to give myself more momentum? Run faster, speed up, okay? So typically you don't change the mass, okay? The most common way to change the momentum is to apply an unbalanced force, so velocity will change. So if I slightly push you, give you a little bit of force, then it is going to be a little bit of momentum, okay? If I apply a lot of force, you're going to have a lot more momentum. We're going to relate force and momentum here in the next slide. Any questions so far? Okay. Ooh, that's even fancier. I didn't know it did that too. Ooh, my fancy computer slides up and down too. Oh, sorry. Impulse. Impulse is something you've probably never really heard of. Now, have you ever heard anyone acting impulsively? What's that mean? What's that mean? Buy something on a whim, yeah. Don't really think about it, just do it. That's a little bit different of a thing of impulse, okay? I know this is very small, but you have to zoom this in. I want to make sure you got those equations big. Impulse is a term that quantifies the overall effects of a force acting over time. Okay. So impulse is force times the change in time. Okay. Impulse has the symbol of J. Don't know why. Impulse has the symbol of J. So I've got a lot of equations on here. Okay. Impulse is equal force times the change in time. Who plays a sport? What does your coach tell you that you need to do a lot? Like when you're hitting a baseball or a softball. No one in here plays baseball. Sorry, Jerry. You need to do what? When you shoot a basketball, you need to do what? When you hit a volleyball, you need to do what? It's the most important part of a shot. You're kind of right. It's your what? It's your follow through. It's your follow through. Okay. Yeah. Now this is 100% a physics problem. Okay. Because your follow through, okay, is your impulse. Okay. Your follow through increases the amount of impulse that you have. Because you're not changing the amount of force you have when you hit a ball, are you? I'm hitting it with the same amount of thing. With follow through or no follow through, I'm not changing the amount of force. But the longer I keep in contact with it is going to be the greater the impulse, okay? The greater the change in time. So that is why the follow through is so important. You know, no matter how hard I hit something, if I just tap it and I don't follow through and I'm only in contact with it for a brief moment, it's not going to have very much impulse, okay? It's not going to have a lot of impulse. The longer I keep in contact with it is going to be the more impulse you're going to have. My big example of this. Who wants to be my test dummy? Come here. Come here. I'm going to smack you. I'm going to smack you. Okay? But I'm going to do it 2 different ways. Okay? You ready? So I'm going to smack you.
Yes. Yes.
I'm not going to apply that much force. I'm not going to apply that much force. Okay? Okay? Did I follow through? Or am I just we're going to talk about bouncing on Wednesday. Okay? But there's really nothing happening there, is there? Okay? Because my force isn't changing, but my change in time, delta, the triangle thing means delta, means change in, okay? It's on there a lot. So the time wasn't that great, okay? Now I'm going to apply the same force, okay? I'm going to apply the same force, but I'm going to increase my time.
What if my head hit the same?
Which one did she move further? Because the force was the same, but the time is what's so important, okay? The time is so important. I know in tennis, thank you, Marnika. In tennis, this is my biggest thing because I have kids, you want to do it and you just want to stop and hit it. And the ball doesn't go and the ball sails. And then we tell them that if you impulse, the longer you keep in contact with it, the more the change in momentum. The impulse equation is very rarely used on its own. Okay, I think you have one homework problem on that today, but it's very, very, very rarely used on its own. Typically, this third dot here is the biggest thing. I know it's hard to see. Impulse equals the change in momentum. You want a ball to have a lot of momentum if you're playing a sport. Momentum is a good thing. Okay, momentum is a good thing. So the biggest thing there is that if we know that impulse is equal to F times delta T, okay, we know it equals the change in momentum. So triangle there is change, okay? So I have this equation's written twice the same way, okay? It's actually written 3 times the same way. Ft equals delta P, Ft equals delta parentheses mv, close parentheses, and F delta T equals mvf minus mvi, or all the, and then finally delta T equals delta P over F, or all the exact same equation, okay? Triangle means change. It's the delta sign, it means change. We're going to use that a lot this year. Anytime you see a delta something, it means change in. So in delta P, change in momentum. Delta T, change in time. And it is always final minus initial, okay? Final minus initial. So in the delta P, mass times the final velocity minus mass times the initial velocity, okay? So all those things are the exact same thing. Now this one here is a little bit different. Okay, I don't know. I should not put that one in the middle, But take out this middle one where my mouse is over, all those are the exact same thing, okay? They're just applying them in a lot of different ways, okay? They're just manipulating them for what you want to do, okay? So an example in there, if you push with the force for twice the time, you impart twice the impulse, and then the big thing in there, you have twice the momentum, okay? You have twice the momentum. You want something to have a lot of momentum physically. You want things to have a lot of momentum when it comes to physics. Bunch of big equations in there. So this is one way we talked about, whether you're playing a sport, following through, things like that are very important for impulse, okay? So is when you talk about stopping distance, okay? Who's taking their driver's permit test? Isn't there a question on there? How far should you be following? How far should you be behind another vehicle? That's a question on there, okay? That's a physics question. The state, I think it's what, 250 feet, 350 feet? It matters whether you're traveling on an interstate or traveling. I tried to go take my chauffeur's test, but didn't go very well. I missed this question like 3 times. What? Yeah, what? Yeah. 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 Yeah, you count. Yeah, there you go. We're about to answer that question today. We're going to answer that question today. How long will it take you to brake? Okay. But when the highway engineers and people design the test, they apply the impulse momentum theorem, which is this slide right here. Okay. This is the impulse momentum theorem. Okay. To determine the stopping time and the stopping distance. Okay. So the example of that on there is a truck. A truck will, a truck with twice the mass of a car, but the same speed will have twice the momentum. So it'll take it twice as long to stop, okay? Twice as long to stop, assuming the brakes are the same, okay? Assuming the brakes are the same. If a truck has 3 times the momentum of something, it will take 3 times as long, okay? Like I went camping this past weekend, and my wife, for the first time ever, drove our horse trailer home. I drove our camper home. She drove our horse trailer home. And the biggest thing I had to talk to her about was, this isn't like stopping your car. You can't just slam on your brakes. Follow further behind because it's going to take you longer to stop, okay? Because the horse trailer weighed a lot. And we had 4 horses in there and some other things in there. So this equation on here is for the stopping distance, okay? Okay, so this equation here is for stopping distance, with delta x being the distance, okay? Delta x being the distance, 1/2 times VF plus VI times the change in time. So that is our equation for stopping distance. Backing it up from the last slide, you're good. From the last slide, if I want to look for stopping time, I'm going to use probably this equation right here, this 4th equation, and just divide it by F, okay? So delta T would be M VF minus M VI divided by F, okay? So that would be for stopping time, okay? For stopping time, this one right here. So with that stopping time question that you just asked is on there, you would use this 4th equation. They're all the same thing, but that would do, so delta T would be equal to M times final velocity minus mass times initial velocity divided by force, okay? Divided by force. All right, how has momentum changed? Okay, to increase momentum, you need to apply the greatest force for as long as possible. This goes back to impulse. I've already talked about this, but that's why follow through is important. The same impulse does not mean the same amount of force or the same amount of time. It is the product of the force and the time. It could be a lot more force or usually a lot more time. So the question here is, I'm sorry, I didn't really mean to give it the answer on there. I meant to have a thing on there. Why would you rather have a dish fall on carpet than a hard floor? Why? That's what's going to happen. The why is what we're concerned with. The answer is on here. The carpet will increase the contact time. So it will reduce the amount of force and the deacceleration, okay? The longer you're in contact with something, the less force that's applied to it at one point in time. It's kind of like what I want to think about. It's kind of like an egg. Has anyone ever put an egg in their hand and broke it? No, you can't do it. No, you cannot. Well, well, I don't know. You cannot physically crush an egg. It is impossible to do it because now you have to have it completely surrounding it, but yes, you cannot completely do that because that egg is strong. Now, can I take it and crack it on the side? Yes, because when I'm trying to surround it all, it spreads the force over a large amount of area. Okay, it spreads the force over a large amount of area. So I can't do that. But when I want to crack it, am I cracking over a whole thing or just one little spot I'm trying to crack it on? One little spot, okay? If I drop an egg, I'm not surrounding the whole egg, am I? I'm only surrounding that one part where it's hitting, okay? Where it's hitting. Try it. All right, last thing to talk about today is law of conservation momentum. Law of conservation momentum tells you that total momentum doesn't change. The law of conservation of anything tells you it doesn't change. Law of conservation of energy, law of conservation of mass, law of conservation of momentum, okay? If you want to change momentum, an impulse must be exerted, okay? But there's going to be things in there. This kind of obeys Newton's third law. So the dashes are an example of the law of conservation of momentum. Before you fire a cannonball, the cannonball is not moving, so it has no momentum. After it's fired, okay, the cannonball has a forward momentum because it's going forward, and the cannon moves backwards. Okay, the cannon moves backwards. That's Newton's third law, equal and opposite. Now, here's my question on this: why does the cannonball move further, go further forward than the cannon goes backwards? The cannon's heavier. Bingo. Bingo. The cannon is heavier. Okay. So still momentum. My speed's not changing. Okay. My momentum's not changing. My speed's not changing. The only thing in there would be the mass. Okay. The heavier the cannonball, the more recoil you're going to have. It's like shooting a gun. Shooting a gun is a prime example of it. I'm going to shoot my 22. Is it going to kick much? Anybody ever shot a gun? Okay. Okay. No, a 22 won't kick very much. Okay. It's a little bitty bullet, very small mass. It has a lot of speed, so it has some momentum, but there's not going to kick much. Okay. It's not going to kick back much. 30-06 or a muzzle loader, a heavier gun or a 45, like a 45 pistol, is a heavier bullet. It's a bigger bullet. So you're going to travel really fast, but it's going to kick back. Like I like to think of my dad did not really pay attention to this when we were hunting one time. First time we got a muzzle loader, and he went to shoot a deer, and he got his eye too close to the scope, split the top of his eye. Because he didn't think of the recoil. So recoil is a momentum thing. Okay, recoil is a momentum. It obeys Newton's third law. Okay, it obeys Newton's third law. But the recoil, the heavier the mass of the object, the greater the recoil it's going to be. Any questions about momentum today? Go ahead. What? Yes, he did. Yeah, it was worth it. I mean, his eye was split. How many questions your homework? I think 25 or 30. Anybody else?